Hey, I'm Karen Lewis. I am part of the research team at NWEA. The presentation you're about to watch is part of the Intro to Map Growth series. The series is intended to introduce the basic principles and the foundational concepts that underlie the map growth assessment. Today, I'm specifically going to be talking about the RIT scale, and I'm going to do this from a non-technical and non-mathematical perspective as much as I can. My goal is not for you to walk away a psychometrician who is now certified to run item response theory models, but instead I want you to walk away with a deeper understanding of the RIT scale so that you're better prepared and more confident in understanding what RIT scores tell us and applying them in your work. And here's what we'll cover in this presentation. We're going to start by talking about the purpose of the map growth test. Next, we'll talk about specifically define what the RIT scale is. And finally, we'll get into the weeds and talk about how an item gets a RIT score, and then finally how a student gets a RIT score. But let's start by talking about purpose. And we need to start by talking about purpose because good assessment always begins with a clearly defined purpose. Purpose really is foundational for all aspects of the measurement process. It impacts how we collect data, how we interpret data, and how we can use data. To help make this a little bit more clear, I want to illustrate with an example. And so we're going to talk about what it means to measure height under different purposes. First, imagine you are measuring height because you are a medical assistant in a pediatrician's office. And it's your job when kids come in for those annual wellness visits to measure their height so they can be placed on a growth chart, which tracks their height relative to population norms for typical growth over time. Doctors collect this information because failing to follow growth curves can be an early indicator of health problems. So in this case, when we're measuring height, a precise height measurement is really important. Imagine instead a different scenario, and you are a carnival ride operator, and you're measuring height because you need to make sure that kids that are tall enough are the only ones allowed on your ride. In this case, you don't care about a really precise measurement of how tall a kid is, but you do want a really accurate measure of whether the child has met the height cutoff or not for safety purposes. So although in both cases we're measuring height, it's obviously a very different scenario to ask the question, how tall are you, versus are you tall enough? And in these two different purposes, we're asking different questions that demand very different levels of precision and produce different data. A pediatrician wants really precise height measurements, perhaps down to the second decimal place in inches. In contrast, asking this question, are you tall enough, really results in a more dichotomous yes-no measurement. In that case, we don't care how high above or how far below the cutoff is. We just want to know with accuracy whether that kid has met the cutoff. Another reason, besides leading to different data, that assessment purpose matters is that validity is inherently tied to purpose. Measures are validated for a very specific purpose, and that established levels or evidence of validity is called into question when those measures are used for other purposes. To push my silly height example a little bit further, if you are that roller coaster operator and you've been measuring kids' height relative to a 42-inch cutoff, and your carny friend at the next ride over wants you to take over and determine whether those kids can ride his ride that has a different height restriction of, let's say, 48 inches, you can't turn around and use your data for that purpose. It wouldn't work. It wouldn't give us the same amount of information. It's not interchangeable because we had a different purpose. So hopefully that starts to paint a picture for why assessment purpose matters. With that in mind, let's talk more in depth now about the map growth assessment and its purpose. So the purpose of the map growth assessment is to precisely and accurately determine a student's achievement and growth over time. What are the implications of this purpose for the map growth test and how the RIT scale were designed? Well, first, let's think about what it means to precisely and accurately measure achievement. Consider a group of third graders. Now, these kids may be in the same grade and maybe of roughly the same age, but of course, naturally, they're going to differ in their math achievement levels. If we think of a grade level standard, some kids will be nearing that standard, some well below, some might be slightly above. Now, most end-of-year summative assessments are intended and designed with the purpose of measuring whether kids meet that grade level standard. And as such, those assessments focus in on a rather narrow band of math achievement, really circling just around above and below that standard. Now, those kinds of tests may provide very accurate information about how students are achieving within that narrow band. But in this case, the goal is to determine if students have met that proficiency cutoff or not. So these tests provide very little information about students that may be above or well below that standard. That's just not what they're designed to do. The items within that more narrow band will be too challenging for our students who are struggling, thus we won't get very good information about them. And those items are likely to be too easy for our students who are excelling, and we'd get less good information about those students. Since the purpose of the MAP growth assessment is to precisely measure a student's achievement level, it would be counterproductive to hone in on a narrow band of the achievement spectrum and focus only on a grade level standard. Instead, what we want to be able to do is meet students where they're at, regardless of whether that's at, above, or below grade level. In other words, we need the assessment to have a very high ceiling and a very low floor, so we can capture all ranges of achievement. Tracking back to our discussion of how different purposes for measuring height led to different types of data and different levels of precision, when we hone in on a grade level standard, we're essentially asking that dichotomous yes-no question. We get a dichotomous yes-no measurement of whether students know enough basic arithmetic to meet that grade level standard. In contrast with the MAP growth test, we want to ask how much basic arithmetic do you know, which means we need to measure achievement with a much higher level of precision so that we can meet kids where they're at. Being able to do this, meet students at their achievement level, regardless of grade level, it's all made possible by the RIT scale. So let's talk about that next. So what is the RIT scale? The scale that underlies the MAP growth assessment is developed using item response theory, or IRT. Now, IRT is a psychometric approach to measurement. There are different types of IRT models, and our analytic approach specifically uses the RASH model, which is where the RIT comes from. You don't need to be a psychometrician to follow this presentation, and we're not going to go into depth. But I do want you to know this basic core concept of what IRT does. In a nutshell, IRT and this approach to measurement takes into account that a person's response to a particular test item is influenced both by qualities of the person as well as by qualities of the item. Applying this to our measurement of achievement, the probability that a student is going to give a correct response to any item on an assessment depends both on that student's achievement level as well as the difficulty of that particular item. Someone with very high math ability will be more likely to respond correctly to math items than an individual with low math ability. And conversely, an item that is very difficult, let's say what's the square root of 983, is less likely to be answered correctly than a very easy item. What is 2 plus 2? To take into account both factors simultaneously, what IRT does is establish a common scale to measure both qualities of people and qualities of items. For students, this scale is a measure of their achievement. Higher numbers on the scale indicate higher levels of achievement. Conversely, lower numbers indicate lower achievement. For items, this scale, when we think qualitatively, what is it telling us? Higher numbers on the scale for items mean the item is more difficult. Lower numbers indicate less difficulty. Let's get slightly more concrete about what this means. So imagine this number line represents the RIT scale, and let's just arbitrarily pick a specific point on the scale, say 200. How would we interpret a score of 200 for a student? Well, a 200 RIT score for a student tells us that this student is getting 50% of items at that specific difficulty level correct. And how would we interpret a score of 200 for an item? A 200 RIT score for an item tells us that this specific item is answered correctly by 50% of students at that precise achievement level. These two things are inherently tied to one another. It can be a little bit mystifying why we hinge on 50%, specifically for educators who are used to thinking about the goal of assessment as a way of learning what students have mastered. We want to see 100% correct. This might make it seem particularly confusing that IRT models hinge at this 50% correct metric. Well, to help make it clear why 50% is this really magical number, imagine I gave these 3 items to a group of 4th graders. This is pretty basic arithmetic, so I'm willing to guess most 4th graders, if not all, get every single item right. Okay, so we know that they can complete these items. Let's give them and follow up with a set of harder items to learn a little bit more about them. We give them these 3 items that are looking at algebra. Our same group of 4th graders is likely to get all of these items wrong. So between these 2 sets of items, what have we learned about our group of 4th graders? Next to nothing. We know the first set of items were way too easy, and the second set of items were way too hard. Our goal is to measure achievement with precision. If students are getting 100% of items correct, we know they've mastered those skills, but we don't know what more they can do. And if students are getting 0% of items correct, we only know that that content is too challenging, but we don't know what they are capable of doing. What we really want to aim for is that sweet spot in the middle. We learn the most about students when we find the edge of their ability, the item difficulty level at which students are getting about half of items correct and half of items incorrect. This is why it's problematic to think of the MAP growth assessment as a mastery test. By design, students are expected to get 50% of items incorrect. There are some key properties of the RIT scale I want you to know. So I've drawn this quote directly from our technical manual, and it sums up 3 key features that are important to keep in mind. MAP growth scores are reported on the RIT scale, which is an equal interval vertical scale that is continuous across grades and is stable over time. So we're going to talk in turn about these 3 concepts of being equal interval scale, a vertical scale, and being stable over time. Let's start with what it means to be an equal interval scale. This simply means that no matter where you are on the scale, the difference between 2 units means the same thing. Returning to our height example, to illustrate this, a 1-inch difference is the same regardless if the kid is very short or very tall. 1-inch difference is 1-inch difference is 1-inch difference. When it comes to the RIT scale, this means that the difference in a 200 and a 210, a 10-point RIT score difference, is the same as the difference in a 270 and a 280. So why do we care so much about the scale being equal interval? Well, we want to be able to use the same scale to quantify achievement all along the spectrum. So we need to be confident that differences between scores mean the same thing, regardless of whether we're talking about very high achievers or low achievers. It's useful to consider a counterexample of what it means to be an unequal interval scale and why that leads to problems. As an example of this, let's look to percentiles, which is a prime example of a non-equal interval scale. The table I'm showing you here plots household income percentiles and the associated annual income. A 5 percentile point difference has a very different meaning depending on whether you're at the low end of the spectrum or the high end. A difference between the 20th and 25th percentiles is about $6,000 of annual income, whereas at the 90th, the difference between the 90th and the 95th percentile is $73,000 of difference in income. So if a politician suggests a tax break equivalent to a 5 percentile point increase in your household's annual income, that would mean very different things to you depending on where you were in the distribution. The next key property to keep in mind is that the RIT scale is a vertical scale. And what it means to be a vertical scale is that we're simply using a common scale to measure achievement across different grades and across different ability levels. This is really critical to the purpose of the MAP growth assessment, to be able to measure achievement precisely and accurately, because we know there is variability within classrooms of kids' achievement levels. Consider the typical 5th grade math classroom. You're going to see a wide range of abilities. Some estimates and research suggest that only about a quarter of students are on grade level. Some students may be 1 grade below, about a third of students, according to some research. Another third may even be 2 grades below. And a non-trivial amount of students are a grade above. We want MAP growth to be able to meet students where they're at. So the scale cannot be tied to a particular grade level. Remember, we want the floor to be very low and the ceiling to be very high so we can capture this range of achievement levels. And a vertical scale makes it possible to do that. The vertical scale is also critical to being able to measure growth over time. You can't make growth determinations in the same way with non-vertical scales. For instance, let's consider comparing students' end of course grades over time with their math RIT scores over time. In the graph on the left, we're looking at a student's performance, let's say in the spring of 5th grade versus 6th grade versus 7th grade. And on the RIT scale, we're seeing they're increasing by a total of 10 points across those two grades. This can be interpreted as growth. Because we're using a vertical scale here, we know that this student's math ability is increasing. In contrast, consider end of course grades, which are a non-vertical scale. If we have a score of 90, let's say out of 100 in 7th grade pre-algebra, decreasing to a 75 out of 100 in 9th grade algebra 2, should we take this to mean that the student is actually decreasing in their math ability? Certainly not. That is not how we interpret end of course grades. But this example is meant to demonstrate that it's only when you have a vertical scale that you can actually make determinations about growth. And finally, the last key property I want you to know about is that the RIT scale is stable over time. This means that the interpretation of the scale yesterday is the same as today is the same as tomorrow. We want a RIT of 220 to mean the same thing as it did 5 years ago and as it will mean in 5 years from now. Now, this doesn't happen by accident, and we'll talk later about how our psychometricians are constantly monitoring the scale to ensure this stability over time and making adjustments as necessary. But to again illustrate why it's important for our scale to be stable over time, let's consider a case where an underlying scale is not stable. And this example is particularly relevant to anyone who's ever bought a pair of jeans, and particularly a pair of women's jeans over the last decade. You may be familiar with the concept of vanity sizing. And at some point, clothing manufacturers figured out that people tend to spend more money when they feel better, and we feel better when we're buying a smaller size. So clothing manufacturers certainly can't edit the size of your waist, but they can edit the correspondence between numeric sizing and inches. So, for example, this chart tracks how the correspondence between numeric sizing and waist in inches has changed over time. A 26-inch waist back in 1970 would have fit a size 12, but in current sizing, a 26-inch waist is a size 0. Clearly, this is not a scale that is stable over time. Sizing now cannot be compared to sizing 10 years ago. And that's painfully obvious to anyone who's tried to buy a pair of vintage jeans and becomes shocked when they realize they have to go up a size or 4. All right, next, let's talk about how an item gets a RIT score. To help you understand how an item gets a RIT score, let's walk through the item calibration cycle. The first step in this cycle, when we have a brand new map growth item, is that the item is going to receive a provisional difficulty estimate. And this comes from the very complicated software known as humans. Our content specialists are the folks that are helping write items. They're also the folks that are helping in this initial process of determining how difficult an item is. So these folks look at a new item and based on their professional judgment, make their best guess about how difficult that item is likely to be and assign the item a provisional RIT score. But our content specialist best guess of an item's difficulty isn't good enough. So we need to use data to empirically determine how difficult that item actually is. And to do that, we need data from test takers. That's where the field testing process comes in. The purpose of field testing is to calibrate the difficulty estimate of each new item that goes into our item bank. What we do in this process is embed new items in the assessment alongside the items that are already used to determine a student's score. And that's how we link new items to the existing item bank. We compare how new items are performing alongside items that have already been calculated and calibrated and use that information to determine an item's actual difficulty. In the field test process, all students participate in this, and students see between 1 to 3 field test items every time they take the map growth assessment. Importantly, these items do not count towards the student's score, and it's a seamless process. Students don't know when they're completing an item that is a field test item. Because we need a lot of data to help us understand an item's difficulty, each new item is administered to at least 1,000 students in the field test process. After we collect that data from at least 1,000 students, we then go and examine how the item performed among our test takers. And I want to show you item response function plots that help us examine that data and determine what an item's actual difficulty is. So what these item response function plots do is show the probability of a correct response to an item against the achievement levels of the students who responded to that item. So in our field test process, we've got 1,000 test takers. We know their RIT score, we know their achievement level, and we look at each of the different achievement levels of the students who responded to that item. How many of students at that level of achievement got the item right? And that's what this plot shows us. When it's working well, it typically follows this S-curve. Now, the horizontal axis on the bottom of the graph here is showing us the achievement level of the students who responded to that item. The vertical axis is tracking what percentage of those students got the item correct. So for instance, if we look here at this X I've placed on our green line, we know that this particular item, when it was given to students at a RIT achievement level of 180, only about 10% of students got that item correct. Remember, we're looking for that magic sweet spot of 50%. We want to know the achievement, the difficulty level is determined by the place at which 50% of students at a particular achievement level got the item right. So in this specific case, for this item, it was students that were at roughly a RIT of 200, 50% of students got that item correctly. So the difficulty level of this item would be determined to be 200. In practice, we compare the actual performance of an item to that theoretical response function to determine the item's fit. And this is a plot from an item that's actually been in the field test process to show you what this looks like. Let me walk through what this graph is showing you. And this comes from an item that did have pretty good fit. First, that green line you see there, the horizontal green line, tells us the probability of a correct response by chance alone. Notice that's at about 25%. So this tells us this item had 4 response options. So by chance alone, we'd expect 25% of students to get the item correct. The vertical gray bar, that's the provisional difficulty estimate assigned to this item by our content specialists. The yellow line, that is our actual observed difficulty level. And that's the point at which 50% of students got the item correct. So this item received a difficulty level of, let's say, about 185. Because students at that achievement level with RIT scores of 185, about half of those students got the item correct. Now let's consider a counterexample of an item with poor fit. Now, each of those little gray circles show you the percentage of students at that achievement level that got the item correct. Notice that in this case, that those percentage correct really deviate from that theoretical S-curve. We've got about 30% of students with a RIT of 180 getting the item right. We also have about 30% of students with a RIT of 240 getting the item right. This item isn't functioning the way we would expect it to. And if an item performs this way and doesn't follow that theoretical S-curve, it's going to get kicked back to our content specialist. It probably needs to undergo some revision. So if the item is not successfully calibrated, we're going to turn it back to our content specialist for review and editing, and then re-enter into the field test process. But if an item is successfully calibrated, then it's added to the item bank. We have a very large item bank of over 40,000 items, and items are continually being added, and items are continually being retired as standards change or removed as they're determined to be problematic. Now, remember how when we talked about the properties of the RIT scale, we talked about how it's stable over time. And we talked about how that stability doesn't happen by accident. And we're continually monitoring items across the entire item bank to maintain the continuity of the RIT scale. Part of this routine maintenance includes regular review of items to check for parameter drift. Parameter drift happens when an item becomes easier or more difficult over time for any variety of reasons. In most cases, item difficulty is highly stable over time. And I'm showing you that here in a graph. In this graph, we have the original item calibration on the horizontal axis. And when item calibration was revisited during maintenance, we have a new calibration based on how that item performed in a new field test process. Notice that those two things are very highly correlated. In most cases, an item's calibration from its original estimate to checking in later in the process, it stays very stable. But there are times when scale maintenance is needed to adjust an item calibration and keep that stability of our scale over time intact. For instance, in 2020, the items on our K2 test were adjusted to address some parameter drift that we were observing between our K2 test and our 2+ test. And this figure is an illustration of that discontinuity that we knew partners were experiencing. What we saw here is that math scores tended to follow this pattern of increasing over time. And starting in about first grade, we know that some students undergo summer slide. Their spring test score is a little bit higher than their fall test score when they return to school after the summer months, having been out of the classroom for a period of time. What we had observed, though, is that between the transition from our K2 test to the 2-5 test, we had a pretty big cliff between spring test scores and fall test scores, bigger than we'd expect based on just summer slide alone. What we found is that the magnitude of this drop was really in part due to parameter drift. So to mitigate this issue, we recalibrated the item difficulty on the K2 test, which means we just went back to the items in the K2 item bank to gauge whether they had become more easy or more difficult with time, and then adjusted the item difficulty as necessary. The result of this process is now depicted by the dotted blue line, and this reflects the adjusted scores on that K2 assessment following recalibration. Notice that after recalibration, we've improved the continuity between these two assessments. We no longer see that large artificial cliff between students transitioning tests between the second and third grade year. So this is an example of the kind of routine maintenance our team does to ensure the stability of the RIT scale over time. All right, finally, let's talk about how a student gets a RIT score. I said several times throughout this presentation that map growth meets students where they're at. How do we do that? Well, we're able to meet students where they're at because the map growth assessment is a computer adaptive test. And what that means is that no two students are ever going to see the same map growth assessment because the test is tailored to a student's individual ability level and individual performance during the testing experience. Item difficulties get adjusted up or down based on how a student is performing. After a student's response to each successive item, the testing algorithm, which is the mechanics behind the map growth test that is select the next item a student will see. Well, that testing algorithm, what it's doing is estimating a student's achievement level continually and updating that estimate throughout the test and selecting the next item with a matching estimate of the student's achievement level, which is driven up for more correct responses and down for incorrect responses. I want to show you what this looks like in practice. So we're going to walk through a simulation of what a, let's say, 22 item test would look like for a student. In this case, students start at item 1 with an item selected for them with a difficulty that is as suitable as possible. For some students who have already taken the map growth assessment, we know their prior RIT scores, and that information can help us select the item difficulty for that first item. In other cases, when we have no prior information about a student, we use their grade level to help us determine the difficulty that would be most consistent with where we'd expect the average student of that grade to be achieving. The system monitors how the student responds to that first item. In this case, the student got that item right. Remember, the test is tailored to a student's individual performance. In this case, if a student got an item at, let's say, roughly a 200 level correct, what do you predict the assessment will do next? Does it make the most sense to give the student an easier item or a harder item? What makes most sense to give the student a slightly harder item? We already know they can probably do and master content at this level, so let's keep going up to understand if they can do more. And that's exactly what the test does. Gives the student a slightly harder item for item number 2. Item 3, again, because they got item 2 correct, item 3 is going to be a little bit harder, and so forth. We're trying to suss out that sweet spot where a student is as equally likely to get an item right as they are to get the item wrong. If a student is continually getting items right, we need to continue adjusting upward to find that edge of their ability. So let's say on this 5th item, the student gets it incorrect. Well, in this case, the test is going to adjust slightly down to give them a slightly easier item. Student gets that item right. Well, let's go back up. That item is incorrect. We'll adjust back down. And this is the process that happens over the course of the test. These slight adjustments getting easier when students get items correct, getting more challenging when students, getting easier when students get an item incorrect, getting more challenging when a student gets items correct to try and find that edge of their ability level. In this case, for this student, we end with a RIT score of about 228. Now, notice in this way, adaptive testing is very economical because we're adapting to a student's achievement level throughout the testing process. It requires much less time to get an accurate result. Because the test is adapting based on performance, we're not wasting time administering items that are far too easy or far too hard. What this means is that the student has a shortened testing experience with equal levels of precision with what we'd expect from longer fixed form tests. Now the test stops. In this example, we just have a 22 item test, but in reality, the test stops when either the maximum length is reached, which is 40 items, plus those potentially up to 3 field test items. Tests may end earlier than that when an acceptable level of precision is reached. So what do we mean when I say precision level? Well, now in this graph, I've added another layer of information. So notice that for each item and its response, we now have a gray vertical bar extending above and below. What that bar is capturing is the standard error of measurement, or SEM. Let's talk about what an SEM is and what it indicates. Measurement is always imperfect. Different sources of noise will always keep us from perfectly estimating a student's true ability level. What we do with the SEM is use it to get a sense of how noisy that estimate is. So what does the SEM tell us? It estimates if this student was tested multiple times, how spread out would each of those scores be around their true score. When SEMs are high, we're not very confident in the precision of that estimate. When SEMs are lower, we feel more confident in that we're getting closer to the true estimate of a student's ability. So when you see SEM or standard error of measurement, what you just need to know is that this is a measure of score precision and lower is better. So to help understand why lower SEM is better, consider these two examples. You have students with identical RIT scores in the graph on the left and the graph on the right, but we have a larger SEM in the graph on the right compared to the graph on the left. So our student on the left is being measured with higher levels of precision than the student on the right. For which of these students would you feel more confident that you actually observed growth between fall and spring? Well, note for the student on the left, their spring score of 222, noting that there might be some imprecision in that estimate. It might be as high as, let's say, 224. It might be as low as 220, but it certainly has no overlap with their fall score. The same is not the true for the student on the right. That same score of 222, the lower bound of what the score actually could be, the reality, is around, let's say, 215. And the upper bound of what that fall score could actually be is about 219. So we have less confidence for that student because we're measuring their achievement over time with less precision. We have less confidence that we're actually observing growth. Now, after each response to an item for a student, their interim ability estimate is updated. And these estimates become slightly more precise with each successive response. So if you look at the value of those SEMs across the test, what do you notice? Well, notice that they're shrinking. The SEM estimate for that very first item is much larger than at the end of the test. That's because with additional information about a student, we're making more precise estimates of their true ability. Lastly, what do you notice in this simulation about the balance between correct and incorrect responses? Remember, we're shooting for that sweet spot, honing in on the student's ability level, where they're is equally likely to get an item right as they are to get it wrong. And so what we see over the 22 items in this test is that we're getting about 50% right and 50% wrong. And when we're hinging at that ability, at the very end, when we get to that final score of 228, we see that right above the 228, the student's getting it wrong, right below, they're getting it right. And that helps us really hone in on that individual achievement level estimate. Now, that example that we just went through was highly idealized in that the student was perfectly engaged with the testing process and was giving full effort on every item. Unfortunately, we know that that's not always the case, and it's really important to monitor a student's engagement with the testing process because test validity and reliability depend on the student being engaged in the test. Student engagement is so important that we have developed processes to check for disengagement. And we do that specifically by keeping an eye out for rapid guessing, or when students are making responses to an item and they do so quickly, we know that's not possible that they would have read that item and gave an effortful response. Well, when this happens, the testing process, the algorithm changes slightly. Let's consider this example where on the third item, we've now detected that the student is giving rapid guesses. After rapid guessing is detected, what I want you to notice here is that for the successive items the student is receiving, notice that we're not adjusting up or down based on their performance as we did in the previous scenario. Once rapid testing is detected, we know that we're getting little information about the test taker's actual achievement level, and so that momentary RIT is not updated and the item difficulty does not change. When this happens, students see this guy, our slow down sloth, which gives the proctor a chance to intervene and help the student re-engage with the testing process. That isn't always successful, and when a student rapid guesses on 30% or more of total test items, the test ends and that score is invalidated. Now, let's zoom back out. These are the 4 topics we talked about in this presentation. Let's tie it all together. First, we talked about the purpose of the map growth and how the map growth assessment is designed to accurately and precisely measure a student's achievement and growth over time, which is made possible by the RIT scale. The RIT scale is the same scale for determining an item's difficulty and a student's achievement level. Items get RIT scores during the field test process, and an item's RIT quantifies the point at which 50% of students at that achievement level answer the item correctly. Conversely, students get RIT scores through the adaptive process of the map growth assessment. Map growth adapts in response to a student's performance to identify the edge of a student's achievement level, and that's the item difficulty level at which they got 50% of items correct. I hope this presentation has been helpful in giving you a deeper understanding of the RIT scale, and I hope it helps you apply RIT scores in your work. Thanks so much for your time and attention today. It was great to be with you.